Hello, and welcome to this presentation on second-order differential equations of the homogeneous type. In other words, each of the differential equations we'll be considering will equal to 0. These differential equations are quite difficult to solve as they require other mathematical techniques to underpin the solutions. For example, we're expected to be able to undertake standard and non-standard differentiation, to solve simultaneous equations, to solve quadratic equations, and also we need awareness of complex numbers. Some reference information: standard derivatives we'll be requiring. Here's the function of y, and here's the derivative dy by dx. And also we'll have to differentiate products. These are non-standard differentials using the product formula shown here. Dy by dx is equal to u multiplied by dv dx plus v multiplied by du dx. Introduction. An equation of the general form a multiplied by d2y by dx squared plus b multiplied by dy by dx plus c multiplied by y is equal to 0, called equation 1 here, where a, b, c are constants, is termed a linear second-order differential equation. When the right-hand side of the differential equation is 0, it's referred to as a homogeneous differential equation. When the right-hand side is not equal to 0, it's referred to as a non-homogeneous differential equation. And we're not covering that type of equation in this presentation. There are various engineering examples of second-order differential equation which are shown on the next slide. Introduction continued. Here are some examples. We've got L multiplied by d2q upon dt squared plus R multiplied by dq upon dt plus 1 upon c multiplied by q equals to 0. This equation represents charge q in an electrical circuit containing resistance R, an inductance L, and a capacitance C in series. Another second-order differential equation is the form m multiplied by d2x upon dt squared plus c multiplied by dx upon dt plus kx equal to 0. This represents a mechanical system where x is the displacement from a fixed point occurring after time t, m is the mass, c is the damping coefficient, and k is the spring stiffness. So that differential equation has been obtained by applying Newton's second law of motion. Third example, d2y upon dx squared plus p upon ei multiplied by y is equal to 0. This equation represents the deflected profile y of a pin-ended strut of constant section having length L, subject to applied load P, where E is the Young's modulus and I is the secondary moment. For example, such an equation can arise when analysing aircraft structures or steelwork structures. Introduction continued. We're going to now look at representing a differential equation in what is termed the operator format. If capital D represents d by dx and capital D squared represents d2 by dx squared, then a general second-order homogeneous equation, shown here, can be written as follows. A multiplied by d2y plus b multiplied by dy plus the cy equals to 0. Or in factorized form, a multiplied by d squared plus b multiplied by d plus c, all in the bracket, and factorized by the y. It's equal to 0. This equation is now stated in what is termed the operator form. You'll see on the following slides we'll use this notation within the second-order differential equation solutions. Introduction continued. Now it can be shown that y is equal to a multiplied by e to the mx is a solution to the differential equation we shown in equation 1 on the previous slide. So given a solution that y equals to a multiplied by e to the mx, we can now differentiate this as it's in standard form and find the dy by dx, or in the operator notation dy, and that's equal to a multiplied by m multiplied by e to the mx. That comes from differentiating e to the ax form from the standard tables. And if we want to calculate the second differential, the d2y by dx squared, or in the operator form, the d2y, then that's equal to a multiplied by m squared multiplied by e to the mx. And again, that's from the e to the ax differential. If we now substitute the above values for dy and d2y into equation 1 above, we form the equation a multiplied by am squared e to the mx plus b multiplied by am e to the mx plus c multiplied by a e to the mx. And that's equal to 0 for our homogeneous equation. If we now factorize on a e to the mx, which is common to every term, we can write the equation as a multiplied by e to the mx multiplied by, in brackets, am squared plus bm plus c, and that's equal to 0. So y is equal to a e to the mx is a solution of the given equation, provided that the am squared plus bm plus c is equal to 0 in this equation. Introduction continued. So note that the am squared plus bm plus c equals to 0 equation is termed the auxiliary equation. And this is a quadratic in m, where the value of m can be found by the use of factorization or the quadratic equation, shown here on the right hand side for convenience. So m is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now since the values of a, b and c are real, then the solution may be one of the following. If the b squared term, under the square root here, is greater than the 4ac term, shown here, then the roots calculated will be unequal. In other words, they will be different. For example, they could be 3 and 4, negative 1, plus 5, etc. If the b squared term is equal to the 4ac term, then the value will be 0, and in solving for m, the roots will be the same. However, if the b squared term is less than 4ac, evaluating we will get a negative value, and the roots in this case will be complex, because we'll be trying to take the square root of a negative number. So that results in complex numbers of the form a plus jb. Here's a generic procedure we're going to use to help us solve the differential equations that are of the homogeneous form, shown here. The first step is to rewrite the differential equation in the form of a multiplied by d2y upon dx squared plus b multiplied by dy upon dx plus cy equals to 0. In most cases the questions might be given in that format, but they may not be. We need to rearrange them into that format. We can then write the above equation into the operator form shown previously. In brackets we've got a d2 plus bd plus c, and that's all multiplied by y is equal to 0. Step 2, we're going to use a notation change here and substitute the value of m for d and solve what's termed the auxiliary equation. So write in the above form as am squared plus bm plus c equals to 0, we're now going to solve for m. We may be able to use factorization at this stage, or we may have to use the quadratic formula. In the third step of the process, the roots of the auxiliary equation will form the type of general solution. So firstly, if the roots are real and different, so the m is equal to alpha and the m is equal to beta, for example, our general solution will be of the form y is equal to a e to the alpha x plus b e to the beta x. 2, if the roots are real and equal, that's m is equal to alpha and m is equal to alpha, then the general solution to form y is equal to ax plus b in brackets multiplied by e to the alpha x. And finally, if our roots are complex, so the m is equal to the alpha plus or minus j beta, our general solution is the form y is equal to e to the alpha x multiplied by, in brackets, a cos beta x plus b sine beta x. So by the end of the third step in this process, we will have the general solution to the homogeneous second order differential equation we're trying to solve. Now in step 4 of the process, if we are given boundary conditions for x, y and y dash, the first differential, we can generate appropriate equations and solve for constants a and b in the above equations shown here in step 3. And we can find what's called the particular solution of the differential equation. You should be aware that this process will involve differentiation of standard and possibly non-standard forms, and also the possibility of solving simultaneous equations to find the a and b constant. Depends on the type of equation we're trying to solve. Example 1. We're asked to determine the general solution for the equation shown here. 2 multiplied by d2y by dx squared plus 5 multiplied by dy by dx minus 3y is equal to 0. We're then given boundary conditions that when x is equal to 0, y is equal to 4, and the first differential dy by dx is equal to 9. And from this we can find the particular solution. So now we will follow the steps from the previous slide. Step 1, labelled A here. If we need to rewrite the differential equation to get all the terms onto one side of the equation, we will. In this particular case, the differential equation is in the correct format. All the terms are on the left hand side and the right hand side equals to 0. So writing in d operator form and factorising on the y, from above we will get 2d squared plus 5d minus 3 inside the bracket, and that's all multiplied by the y. So we factorise this equation on the y and wrote it in d operator format. Step 2, labelled part B here, we're now going to substitute the m symbol for d in the above equation and write the auxiliary equation as 2m squared plus 5m minus 3 is equal to 0. This is now a quadratic in terms of m. I'm going to solve by factorisation here. So factors of the 2m squared term could be written as 2m and 1m, and factors of the negative 3 constant can be written as negative 1 and positive 3. So cross multiplying the above values, 2m multiplied by positive 3 is positive 6m, and 1m multiplied by negative 1 is negative 1m. Adding them up we get 5m, and that's the middle term above, so we've got our solutions. So the factors in this case will be 2m minus 1 and m plus 3, and they equal to 0. If we now want to solve for the roots, we simply equate each of the factors individually to 0 and solve the resulting equation. So considering 2m minus 1 is equal to 0 and rearranging, m is equal to a half, that's our first root. And then considering the second factor, m plus 3 is equal to 0 and rearranging, m is equal to negative 3. So we now write the roots in terms of alpha and beta. So alpha in this case is the half, or 0.5, and beta is negative 3. Example 1 continues. Step 3, labelled C here. Because the roots are real and different, the general solution from the previous slide is as the form y is equal to a e to the alpha x plus b e to the beta x. So for the question we're trying to solve here, the general solution will be y is equal to a e to the 0.5x plus b e to the negative 3x. I've called that equation 1 for reference. Step 4, D here, we're imposing now the boundary conditions given in the question. So from the question we know that when x is equal to 0, y is equal to 4, and dy by dx is equal to 9. That's the first differential equal to 9. So now imposing the boundary condition when x is equal to 0, y is equal to 4. So inserting 0 into the right hand side of the equation where we see an x, and putting the 4 on the left hand side of the equation where we have the y. So the next line of the equation becomes 4 is equal to a e to the 0 plus b equal to 0. Don't forget anything to the power of 0 is 1. So that's basically 4 is equal to a plus b. I've rearranged the equation to make a the subject, so a is equal to 4 minus b, and I've called that equation 2. If we now differentiate equation 1 above, using standard forms here, we find we get dy by dx is equal to a multiplied by the 0.5, e to the 0.5x, plus b multiplied by the negative 3 multiplied by e to the negative 3x. That's just using the standard form from our standard differential tables. Tidied up on the next line, dy by dx is equal to 0.5a multiplied by e to 0.5x minus 3b multiplied by e to the negative 3x. Again, we can impose our boundary conditions. We know when x is equal to 0, dy by dx is equal to 9. So inserting these values into dy by dx equation, on the left hand side again we have 0 for the x term, and on the right hand side we have 9 for the dy by dx term. Again, noting that e to the 0 is 1, we can simplify the equation to 9 is equal to 0.58 minus 3b. And I've called that equation 3 for reference. Now we substitute equation 2 into equation 3. So we now have 9 is equal to 0.5 multiplied by equation 2, which is 4 minus b minus 3b. On the next line we simply expand the brackets and then collect the terms together. By rearranging, we find that b is equal to negative 2, and then back substituting the value of b into equation 2 above, we find that a is equal to 6. I will let you review the arithmetic used here to find constants a and b. Finally, we can write down the particular solution, which in this case will be y is equal to 6 e to the 0.5x minus 2e to the negative 3x. I would encourage you to stop the presentation for a moment and review that slide so you clearly understand how the general solution has been achieved and also the particular solution here. Exercise 1a, we're asked to find the general solution of the equation given in the question shown here, and also find the particular solution when we're given the boundary conditions of t is equal to 0 and y is equal to y dash, which is equal to 3. We're using the functional notation here, so y dash is the first differential and y double dash is the second differential of t in this case. There is a hint in the question that says we need to differentiate a product here, so we need the product rule from the previous slide. The answer here is shown in the square brackets. Exercise 2, we're asked to solve the differential equation shown on the right hand side here to find the particular solution. So again, we are given boundary conditions in the question. X equal to 0, y is equal to 3, and dy by dx equal to 7. Again, the answer is shown in the square brackets. I would encourage you to stop the presentation and attempt exercise 1a and 2a. The full work solutions to exercise 1a and 2a are shown on the following slides. Exercise 1a, we're asked to determine the general solution of the equation shown here on the right hand side, and then furthermore find the particular solution given the boundary conditions that t is equal to 0, y is equal to 3, and y dash is equal to 3. Don't forget in this question y double dash is equal to d2y by dt squared, and y dash is equal to dy by dt. Y is the function of t. So step 1 of our process A, we're going to rewrite the differential equation. Notice the equation given in the question is in the correct form because all the terms are on the left hand side and it equals to 0 on the right hand side. That's the form we need to start from. So we're now going to write that into the operator form, factorising on the y. So the 9 double dash becomes 9d squared, the minus 24y dash becomes minus 24d plus 16, all in the bracket, multiplied by the y. And that's still equal to 0. In step 2, label B here, we're now going to substitute m for d and solve what's termed the auxiliary equation. So now the auxiliary equation is 9m squared minus 24m plus 16, and that equals to 0. Solving for m, we're going to use factorization again in this particular case. So the 9m squared can be factorized as 3m and 3m, and the constant 16 can be factorized as -4 and -4. Cross multiplying, we get -12m minus 12m, so that's -24m, and that's the term in the middle of the equation. So we've solved the equation using factorization. So the factors in this case will be 3m minus 4 in one bracket, and then 3m minus 4 in the second bracket. They're equal to 0. Obviously, solving the roots here, we find that the m is the same in both cases. So m is equal to 4 upon 3 and m is equal to 4 upon 3. Our two roots are the same. So right now it's alpha is equal to 4 upon 3 and beta is equal to 4 upon 3. Exercise 1a solution continued. Part 3 here. Now, because the roots are both real and the same, the general solution from our previous slide will be y is equal to at plus b in a bracket multiplied by e to the alpha t. So the general solution for this particular question will be y is equal to at e to the 4t divided by 3 plus be to the 4t divided by 3. And that's labelled equation 1. So there's our general solution. Now in step 4, is part D here, we're going to impose the boundary conditions given. We're told that when t is equal to 0, y is equal to 3, and dy by dt is equal to 3. So imposing the first condition, t is equal to 0, y is equal to 3. So on the right hand side of equation 1 above, where we have a t, we now replace that with a 0. So these locations we have the value of 0, and the y on the left hand side is equal to 3. So noticing that the first term on the right hand side will be 0 because we're multiplying by 0, we're left with the equation 3 is equal to b e to the 0, and of course e to the 0 is 1, so b is equal to 3 in this case. So there's our first constant. We now need to differentiate equation 1 to find the dy by dt solution in this particular case. So y is equal to a multiplied by t e to the 4t divided by 3 plus 3 multiplied by e to the 4t divided by 3. Now notice that the a multiplied by t e to the 4t divided by 3 is a product. We've got two functions of t here. T is multiplied by e to the 4t upon 3, so they're both functions of t. Should you need to recap the use of the product formula, there's a previous presentation related to differentiation of products, quotients and functions of functions. I would encourage you to review. So to apply the product formula, we need to first of all define a u term and define a v term. So if we let u is equal to t in this particular case, then du by dt is equal to 1, standard differential. And if we let v is equal to e to the 4t upon 3, then differentiating to find dv by dt, that will become 4 upon 3 multiplied by e to the 4t upon 3. And again, that's a standard form of e to the at in our standard differential tables. Now inserting the values of u, du by dt, v and dv by dt into the product formula, we find the following. So solving for dy by dt, and we're differentiating this part of the equation first of all. We have a multiplied by, in the brackets, the u term which we defined as t, multiplied by the dv by dt term, which is shown here, and then we add to that the v term multiplied by the du by dt term. Now differentiating the second term, the plus 3e to the 4t, that standard form of e to the ax, and that differentiates to plus 3 multiplied by 4 divided by 3, e to the 4t upon 3. Tidying up on the next line, dy by dt is equal to 4a multiplied by t e to the 4t upon 3, that's divided by 3, and then we add to that the a e to the 4t upon 3 plus the 4e to the 4t upon 3. On the next line we simply factored on the e to the 4t upon 3, and now we impose the boundary conditions. We know that when t is equal to 0, dy by dt is equal to 3. So placing the 0 wherever we have a t on the right hand side, and on the left hand side that equals to 3. So our equation becomes 3 is equal to e to the 0, and in bracket 0 plus a plus 4. So 3 is equal to a plus 4, so rearranging a is equal to negative 1. So in this case the particular solution is y is equal to negative t e to the 40 upon 3 plus 3e to the 40 upon 3, or rewriting y is equal to, in bracket, 3 minus t multiplied by e to the 40 upon 3. Exercise 2a, we're asked to solve the following differential equation and find the particular solution and given the boundary conditions x equals 0, y is equal to 3 and dy by dx equal to 7. So here's the equation we're trying to solve, the second order homogeneous differential equation. So in our step 1 we need to rewrite the differential equation. Notice it's not quite written in the correct format. We do have all the terms on the left hand side and it equals to 0, so that's correct. But notice that this term here, the d2y by dx squared, should really be the first term in the equation for clarity. So I'm just going to rewrite that. So the first term is d2y by dx squared plus, now the 6dy by dx term is stated, plus the 13y, and of course it's got to equal to 0. So now rewriting in the operator form, that becomes d squared plus 6d plus 13 in a bracket multiplied by y is equal to 0. In step 2 we're going to now substitute m for d and solve the auxiliary equation. So m squared plus 6m plus 13 is equal to 0. We're going to solve for m. In this particular case I'm going to use the quadratic formula, and our equation is the form y is equal to ax squared plus bx plus c, or in this case the y is equal to 0 and the x are equal to m. Here is the quadratic formula. M is equal to the negative b plus or minus the square root of the b squared minus 4ac all divided by 2a. Note in this case the a is equal to positive 1. There's a 1 written here in front of the m we do not usually write. The b in this case is positive 6 and the c is positive 13. That's all extracted from this equation here. So now inserting the values of a, b and c into the quadratic form and solving for m, what we notice here is we get a negative term under the square root when you undertake the arithmetic. So we're looking at complex solutions here. So following the arithmetic through, you should find that m is equal to negative 3 plus or minus j2. It's back to complex notation. So writing that in terms of alpha plus or minus j beta, then alpha in this case would be negative 3 and beta would be positive 2. I would encourage you to review the calculations here and clearly understand how we end up with the complex solution. Exercise 2a continued, the third step. Noting that the roots in this case are complex, the general solution from our previous slide will be y is equal to e to the alpha x multiplied by, in brackets, a cos beta x plus b sine beta x. Again, that's taken from the previous slide showing the various solutions for the different type of roots we can find. So in this particular case, y is equal to e to the negative 3x and in brackets a cos 2x plus b sine 2x. Call that equation 1, and that's the general solution. Step 4, we're now going to pose the boundary conditions given in the question when x is equal to 0, y is equal to 3 and dy by dx equal to 7. So using the first condition, when x is equal to 0, y is equal to 3. So on the right hand side we simply place the value of 0 for x terms. On the left hand side we have 3 for the y term. Evaluating, we find that the a is equal to 3 in this case. Now we need to differentiate equation 1 above, but we need to be careful because again this is a product. We have a function of x, the e to the negative 3x, and that's multiplied by functions of x. The 3 cos 2x is a function of x, so there's a product here, and also the e to the negative 3x multiplied by the b sine 2x is again a product. Exercise 2a continued. Repeated equation 1 from the previous slide for convenience. So applying the product formula, we'll let u is equal to e to the negative 3x, differentiating du by dx is equal to negative 3 e to the negative 3x. And we'll let v in this case be the 3 cos 2x plus the b sine 2x, the bracketed term. Finding dv by dx, standard forms here, we get negative 3 multiplied by 2 sine 2x plus the 2b multiplied by cos 2x. Those are standard forms differentiating cos ax and sine ax. Again, these are covered in a previous presentation on differentiation. So tightening up the equation, we equal to negative 6 multiplied by sine 2x plus 2b multiplied by cos 2x. So what we've done there is differentiated a product using the product formula shown here. Exercise 2a continued. So from the previous slide, we're now going to insert the u, the du dx, dv and the dv dx terms into our equation. So dy by dx, and from the previous slide, this was the u term multiplied by the dv dx term. We add to this the v term multiplied by the du dx term. What we've done on our next line is bring the negative 3e to negative 3x to the front of this bracket here. Our next line we simply factorised on e to the 3x. Notice use of the big square brackets here. On the next line we've simply expanded this term in the brackets, so that's negative 3 times 3 is negative 9 cos 2x, and negative 3 multiplied by the b is negative 3b sine 2x. What we do on the next line is factorise, so considering the positive 2b cos 2x and the negative 9 cos 2x, we can factorise on the cos 2x and have 2b minus 9 in the bracket. And then we can factor on the sine 2x, so these two terms now factored by sine 2x, so there's a factor there, and inside the bracket I've got 3b plus 6. Notice the negative is outside the bracket because they're both negative terms here, so I need the positive inside the bracket. Imposing now the boundary conditions when x is equal to 0, dy by dx equal to 7 from the question. So inputting the 0 wherever we see an x, and that's equal to the dy by dx is 7. Evaluating, we find that b is equal to 8 in this case. So our particular solution for this problem is y is equal to e to the negative 3x, and in brackets 3 cos 2x plus the 8 sine 2x. Again, I would encourage you to review that slide at your own pace, clearly understand how we place the values into the product formula, simplified, solved for constant b, and then stated the particular solution. Here are some further exercises related to contextualized problems in mechanical and electrical engineering, but essentially the same kind of solutions are required as shown on the previous slide. In exercise 1b, the differential equation is shown here in the correct format with all the terms on the left hand side, but be careful with exercise 2b. This is shown as d2v upon dt squared is equal to omega squared multiplied by v. Now be careful here, you need to move the omega squared v to the left hand side of the equation so that the differential equation equates to 0 before you commence the solution process. So be careful of that. With all the homogeneous equations, you must have the equation equal to 0 before you start the solution. And exercise 3b is another contextualized question, electrical context. Notice you're given the values of r, l and c that you can use in the equation. So here's the constant r, l and c in the equation. Also be careful that the capacitance C is given in terms of microfarads. Do account for the micro prefix there. Again, with all the exercises we're given boundary conditions so we can find our particular solutions. The answers are shown in the square brackets below each of the exercises. I would encourage you to stop the presentation and attempt these exercises, but a solution for exercise 1b is shown in full on the following slides. Exercise 1b, we're given the equation for a simple harmonic motion of a body oscillating at the end of a spring is given by the differential equation d2x upon dt squared plus 100x is equal to 0. The displacement is x and it's measured from the equilibrium position after time t. which is in seconds. We've got to find x in terms of t, given the boundary condition that t is equal to 0 when x is equal to 2 and dx by dt is equal to 0. We've got to find the particular solution. So in step 1, we need to rewrite the equation in d operator form. Notice the equation as given is in the correct format because it equates to 0, but in d operator form the equation we've written is d squared plus 100 in brackets multiplied by x is equal to 0, or in this case d is equal to d by dt. Step 2, we're going to substitute m for d and solve the auxiliary equation. So from above we get m squared plus 100 is equal to 0. Now because there's no b term in our quadratic equation, this becomes a direct solution for m. So rearranging, m is equal to the square root of negative 100, which can be written as the square root of, in brackets, negative 1 multiplied by 100. Taking the 100 outside of the square root sign, we can write that as plus or minus 10 multiplied by the square root of negative 1. And don't forget from our complex number work, the square root of negative 1 is written as j. So we can write the solution as plus or minus j10. So in this particular question, m is equal to 0 plus or minus j10. That's of the form alpha plus or minus j beta. So alpha in this case will be 0 and beta will be 10. Exercise 1b continues. Step 3. Now since the roots on the previous slide are complex, our general solution from our previous table will be y is equal to e to the alpha t multiplied by, in brackets, the a cos of beta t plus b sine of beta t. So in this particular case, knowing that alpha is 0 and beta is 10, the solution is y is equal to e to the 0t multiplied by the a cos of 10t plus the b sine of 10t. E to the 0t is 1, so that simplifies to y is equal to a multiplied by cos of 10t plus b multiplied by the sine of 10t. I've called that equation 1, the general solution. And in step 4 we're going to impose the boundary conditions given in the question, that when t is equal to 0, x is equal to 2 and dx by dt is equal to 0. So when t is equal to 0, x is equal to 2, so replacing t with 0 in equation 1 above, we get 0 here and 0 here. And that equates to the x is 2 on the left hand side. Solving, we find that a is equal to 2 in this case. So we now need to differentiate equation 1. So equation 1 is x is equal to the a, which is now 2 cos 10t plus the b sine 10t. So dx by dt is equal to 2 multiplied by the negative 10 sine 10t, from our standard tables, plus b multiplied by 10 cos 10t. Simplifying, that becomes negative 20 sine 10t plus 10b cos 10t. All I've done on next line is slightly rearrange the equation to put the positive term before the negative term. Now imposing the boundary conditions, when t is equal to 0, dx by dt is equal to 0. So placing a 0 wherever it says t, and we get 0 on the left hand side because the dx by dt is equal to 0 in this case. Evaluating, we find that b is actually 0 for this particular exercise. So simplifying, our particular solution becomes x is equal to 2 cos of 10t, and the unit is the meter. There are some tutorial questions I would encourage you to undertake. They're all written in the correct format, and that you have all the terms on the left hand side and it equates to 0 on the right hand side. Solutions are shown in the square brackets. Further questions shown here, and we're asked to find the particular solutions because we're given boundary conditions in all the questions. Again, they are all rearranged in the correct format. They all equate to 0, which of course is the starting point for all our homogeneous equations. Further contextualized questions here, answers are shown in the square brackets on the right hand side. Here's a bibliography used to generate the presentation, an excellent engineering maths textbook for technician engineers. I hope this presentation has been of interest to you, and thank you for viewing.